hierarchical agglomerative clustering. And this joint work with Ichio Yan, Julian Lakshman here. Okay, cool. So, right. So this is the work on clustering. Oh, is it changing? I don't know why. Is it okay that that doesn't change back there?
Yeah, it's okay.
Okay.
Oh. Yeah, it's not. It's not changing on Zoom. Yeah.
Oh, really? Oh, let me share again. All right, cool. Now it's there. Cool. So yeah, this is the work on clustering. So what is clustering? It's a type of a supervised machine learning method. And the goal of clustering is to group similar objects together. And has really wide applications across pattern recognition, image analysis, information retrieval, as well as the other applications listed here. So you can imagine, for example, our MRI graph, you can use clustering to detect tumors, that kind of stuff. At the bottom here, we have an example of clustering points in two-dimensional space, where you can see that points that are similar in the sense that they are closer to each other in the Euclidean space are clustered together, meaning on the right side, they have the same colors. So in general, yeah,
your working assumption. So your working assumption is that you have enormous amount of parallelism, right?
Enormous amount of boundaries.
Parallelism.
You don't have to, or in the work, if you want to analyze the depth, it's the time that it took if you have infinite workers, but you don't have to have infinite work. Even if you only have like.
No, I'm not talking about infinite. You need to have a lot of parallelism for starting to cluster things, right? Because if you don't have a lot of parallelism in pyramid type modeling, you don't have anything to work with.
Even if you only have like by parallelism, you mean like the number of workers?
No, yeah. I mean in the swap depth model.
Yeah.
If you had completely free from allocating operations to totals.
Yeah.
In this model,
yeah,
a lot of parallelism. Otherwise,
yeah.
Okay, no, just the assumptions are important.
Yeah, that's true. But for this work, it would also work. Or like work depth model, like you try to optimize both work and depth, right? So even if you only have a single thread, meaning the work is the same as time, it would still work. But of course, if you have a lot of parallelism, then you achieve your running time will be similar to the depth. So yeah, in practice it would work, but of course the depth bound, or if you want your running time to match the depth bound, it only happens when you have a lot of parallelism, as you said.
Okay, so your assumption is that whatever number of clusters you can support in your hardware, now your job is to make the best use of it.
We're trying to discover clusters from the data, yeah. Right? So I mean, I think the setting is pretty similar to the work that we're doing, right? So it's a single multi-core machine with like 100 cores, and then you have a large amount of data. So typically, there's enough parallelism to completely utilize your clusters.
Okay, good.
All right, cool. Okay. So yeah, so in general, my work is to use parallel computing to accelerate clustering. But I don't know why it's not. I don't know why Zoom is not doing its work. Okay. And I've been in my work, you have to use the input data, like the graph data or the metric or vector data, and then you input that into some clustering algorithm or some clustering framework, and in the end you get an output which is the cluster graph data or the cluster metric or vector data. So in this work, we're going to specifically focus on the hierarchical agglomerative clustering. I don't know why that's not updating there, so I'd have to just reshare every time I change slide. All right, cool. So in the rest of the talk, I'll first talk about the background of this hierarchical agglomerative clustering, and then I'll talk about our parallel hack framework, which include our round-based parallelization and arrange search to increase efficiency and the cache optimization. And finally, I'll talk about some experiments. At the very end, if we have some extra time, I'll briefly talk about some of the other parallel clustering or algorithms that have been worked on as well. Okay, so the background of hack. So hack, similar to other clustering algorithms, group similar objects together, but it groups objects at all resolutions. So in the sequential version, you iteratively merge the closest pair of the intermediate clusters and produce a tree that represents clustering results at different scales. And the input is a dataset and a linkage criteria that specifies how distances between clusters are computed. And for example, one example linkage criteria is called a complete linkage criteria, where the distance between two clusters is the furthest distance between points in the two clusters. For example, here, the distance between those two clusters would be the distance between those 2 points, because they're the furthest between all pairs of points in the two clusters. And finally, the output is a tree called dendrogram. So in a second, I'll give an example of running sequential hack and what a dendrogram looks like. But so far, any questions here? Okay, cool. So I'll proceed. So now, as I promised, I'll give an example of running the sequential hack algorithm. So what you do is you have to first compute the point watch distance matrix. And now for this example data set that have a fixed point, it would look like the distance matrix over there. And then initially we initialize each point as a singleton cluster. So each point is in its own cluster. And then in each of the n-1 rounds, you merge the nearest pair of clusters and you update the distance matrix and the dendrogram. So for example, in the first round, the nearest pair of clusters is CD, and you can find that by seeing that root square 2 is the smallest number in the total distance matrix. So you merge CD and you also update the dendrogram to create an internal node that's for CD, and the height of CD is the same as the distance between C and D. And now you need to update the distance matrix. So this distance matrix is updated by something called the Length-Williams formula. And in complete linkage, this is actually just taking the max between two distances. So for example, here, when you merge CD, now you need a distance between the merged cluster CD to all of the other clusters. So here, if the distance between CD to A is root square 7 or root square 17 and root square 13, the updated distance is the max between them, which is root square 17. So this max is the Length-Williams formula for complete linkage, right? And then you do that for all of the other clusters as well. And you've updated your dendrogram, your distance matrix. So now in the next round, again, you merge the closest pair of clusters, that's A and B there. So we merge it, you update the dendrogram, and you update the distance matrix. Okay. So I just check, is it updating on the Zoom? Oh, okay, maybe there's some problem. I'll just, should we try to fix it? I don't know why.
If you maybe just open it as a window and share your entire screen, maybe that'll make it work. I don't know, just a thought.
Yeah, actually that's what I'm doing right now. Oh, okay, looks like it's working right now. Okay, is it working? Okay, cool. Okay, so yeah, so in the third round, you again merge the closest pair of clusters. Now it's between the merged cluster A, B, and E. And again, you create a dendrogram here. And again, the height here is actually the distance between A and E. That's the furthest pair of clusters. Sorry, are you having a question or just okay? All right, cool. So then in the next round, you merge A, B, E, and C, D. And in the last round, you merge everything, and now you finish the sequential hash algorithm. So for this algorithm, it requires n-squared log n work and quadratic space. And now you've obtained a dendrogram from the cluster. Now the question is, okay, how do I actually get a clustering from this dendrogram? So actually it's pretty easy. You just need to choose a place to cut the dendrogram, and then each of the subtrees forms a cluster. So if you cut the dendrogram somewhere here between 3 and 4, you get 3 clusters: A, B, E, C, D, and F. And of course, if you cut the dendrogram at different heights, you'll get clusters at different resolutions. So this is how the hack algorithm or many other hierarchical agglomerative or hierarchical clustering algorithms give you clusters at different scales. So here is just an animation of cutting the dendrogram at different heights, giving you different clusters. So the color points are pointing merged clusters, and the back dots here are just singleton clusters. And you can see that as you cut at higher thresholds, you'll get fewer clusters, but larger clusters. Just show that again. Okay, so far, any questions about the setting? No? Okay.
Yeah, I would like to ask a question at the end, but just for you to understand where I'm coming from. I think if you look at computer science over the years, it has moved to higher and higher abstractions. And here, what you seem to do is go in the complete opposite direction. You expect the programmer to really uncover, I expect what you will be doing later, the architecture, and do all this enormous amount of sweating in order to fit it for a given architecture. That the other question, of course, is robustness to different generations of architecture. But the amount of work here is completely the opposite of the old times where people worked on C, and now they work on Python, which is much higher level. And here you put something in the complete opposite direction, which you can do for one problem. But I think that the message beyond the very narrow group people who work on that is, I'm not sure they will be able to buy it. So that's I ask you to refer to it at the end. I don't want to disrupt you, but I'm just want to share with you what goes on in my mind when I hear it.
Yeah, maybe you could talk at the end about how this algorithm maps to other architectures. Like, yeah, that would be, I think you're working on that too. So that would be useful to share at the end. Yeah,
I can address that at the end after we finish the talk. Yeah, also I think the techniques we're using can be broadened to other problems as well as other computer architectures. But yeah, in the snippet work, we're only evaluating on the CPUs.
Yeah, I didn't want to disrupt the flow of your presentation. I just wanted to share with you a question.
Yeah. Cool.
I will
be
interested in it.
Yeah, that's a very good question. Thank you for raising it. Okay, cool. So yeah, we're gonna later introduce our techniques, but just to fast forward a little bit. In the end, we get a new hack algorithm that requires only linear memory and are scalable to larger data sets. Remember, the previous algorithm requires quadratic memory, so that would be really not scalable to large data sets. And also, our parallel algorithms achieve up to 110 times speedup and requires up to 237 times less space in practice than the previous parallel hack algorithms. About the work, so unfortunately, the worst case work is cubic, which is not as good as sequential algorithm. But in fact, in practice, the work is only close to the square, the n square, and we have some more fine-grained complexity analysis in our paper to show why this is the case. And also, our algorithm is orders of magnitude faster than other n square work algorithms, even if you just run our algorithm sequentially. Okay, so the way that we accelerate the algorithm is actually using something that's called the nearest neighbor chain. And this nearest neighbor chain is a linked list of nodes where each node represents a cluster and it points to its nearest neighbor, or we could call it a successor. So in this case, the orange arrow is showing you a nearest neighbor chain. And at the end of the nearest neighbor chain is a reciprocal nearest neighbor pairs. So here, the end of the nearest neighbor chain, C and D, they are a reciprocal nearest neighbor pair because C is D's nearest neighbor and D is C's nearest neighbor. And you can grow a nearest neighbor chain by keep looking for the nearest neighbor of the last node in the chain. So here, if you start your nearest neighbor chain at node F, you grow the nearest neighbor chain to find E because E is F's nearest neighbor, and then find D, which is E's nearest neighbor, and so on and so forth. In the end, you finish growing the nearest neighbor chain when you find a reciprocal pair of nearest neighbors. Okay, so I'm going to first show a sequential nearest neighbor chain algorithm and then explain how we parallelize it. So initially, the beginning of the algorithm is the same. You still get distance matrix, and then you initialize each point as a singleton cluster. But here, instead of merging the global closest pair, you grow the nearest neighbor chain until you find the reciprocal nearest pair of clusters, and you merge the reciprocal nearest pair of clusters. So this makes the algorithm a lot more flexible because now in the first round, you can either merge A, B, or C in the first round, depending on where you start to grow your nearest neighbor chain, right? So just to make it a bit different from before, let's suppose we now choose to merge AB first. You merge AB, and you update your distance matrix similar as before, right? And now you grow the nearest neighbor chain again, starting from AB. And now you find CD as the nearest neighbor, you merge it, you update distance matrix, and so on and so forth. In the end, you'll actually get the exact same dendrogram as before, even though the orders of merger is different right now. So this algorithm improves upon the previous one because now it only takes the quadratic time and but also quadratic space. And a restriction here is that the linkage criteria must satisfy the reducibility property, which ensures that the nearest neighbor of a cluster does not change unless one of the cluster merge is its nearest neighbor. So this might be a bit hard to parse out as a specific example of what does this mean. So specifically, what this means is that now, even though both AB and CD can be merged in the first round, but even if you merge AB, C's nearest neighbor is still D, and D's nearest neighbor is still C. So eventually, C and D are gonna merge. So regardless of the order of merges, you'll always get the same dendrogram. That's because of this property. And the good news is that actually many popular linkage criteria satisfies this reducibility property. Okay, so before I go further into details, are there any questions so far about the nearest neighbor chain algorithm? No? Okay. Cool. So now I'll start talking about our parallel hack framework and our round-based parallelization. So one important insight is all of these reciprocal nearest neighbor pairs actually can be merged simultaneously, and that's how you can parallelize the algorithm. So to naively kind of apply this insight, what you can do to the algorithm is you say, while more than one cluster remains, I now in parallel merge all reciprocal nearest neighbors by maintaining multiple nearest neighbor chains, right? And then I update the cache tables. So this cache table is something that we'll explain in a second. But basically, it's similar to the distance matrix that maintains the intercluster distances. Okay. So now there's some more optimization that we can do. In fact, what we did is first, instead of computing and store all of the quadratic pair of distance matrices, we only store some of them in a thing called cache table, and that's how we achieve to use only subquadratic memory. And also in this part, we use a technique, range search, to find the reciprocal nearest neighbors more efficiently while maintaining the nearest neighbor chains. And specifically, so for this step, we use something called the KD tree. And because of the curse of dimensionality, this is optimized for low-dimensional data sets in Euclidean space. As in high-dimensional space, you need to use some other data structures because KD tree does not work too well in high-dimensional data sets. Okay, so this is an example of rerunning the parallel hierarchical agglomerative cluster algorithm. So the same data set as before, and as we said, initially you will have all points in similar clusters. So you can just initial the nearest neighbor chains by just doing a regular nearest neighbor search, and now you obtain all of the nearest neighbor chains. And now you have two reciprocal nearest neighbors, A, B, and C, D. So you can merge both of them in the first round. And then now you again find the grow the nearest neighbor chains from A, B, and C, D, and that's what we got. And notice that because of the reducibility property, the nearest neighbor of F does not change, so we do not have to recompute the nearest neighbor of F. And you keep the nearest neighbor chains, and finally you would again obtain the exact same dendrogram. So notice that now we've reduced one round in this parallel framework. So even though we only reduced one round in this example, that's because this data set is pretty small, but if you have a larger data set, you would be able to reduce much more rounds. Any questions so far?
Is there similarity between this and minimum spanning forest?
Yes, actually, if you use a single linkage criteria, where distance into clusters is the smallest distance between all pairs clusters, this would be the same as you create a Euclidean minimum spanning tree.
And so what are you doing beyond that?
So yeah, so in this case, we are not using the the smallest linkage criteria. We're using the complete criteria as well as there's something called average linkage criteria and a worst linkage criteria. So for all of those different linkage criteria, they are not equivalent to the minimum spanning tree, Euclidean minimum spanning tree anymore. So you couldn't just use the minimum spanning tree on.
I didn't catch the names of the
Yeah. So let me see.
Talking about it later, that's fine. I didn't catch the terms.
Oh yeah, so it's basically the different names of the different linkage criteria. Like for example, right here, the distance between those two clusters is the distance between C and F. That's what complete linkage means. In minute or your single linkage, distance between like this cluster.
No, but the algorithm says round, so
Hmm?
even in the minimum spanning forest algorithm, you have round. So clearly the linkages in the first round are different than the ones in the second. Because you keep clustering.
I see. So I guess you can also use this algorithm to solve the minimum spanning tree problem, but not all algorithms that solve minimum spanning tree algorithm can be used to solve this problem. Maybe that's a better answer because in this problem, due to the different linkage criteria, it's more complicated to find efficient algorithms to actually grow the nearest neighbor. Like for example, in this stage, whether or not this cluster or this cluster is the nearest neighbor of F is not that obvious, right? If you are disputing a minimum spanning tree, you could say, okay, I just find the nearest neighbor of F, and that's E. So the nearest cluster to F is this. But in this case, since the distance between F and those two is the furthest point between them, then the nearest neighbor of F is not that obvious. Does that make sense?
I'm not sure. But in any case, I think it's important to order ideas here and say where you have an idea contribution. And because the proximity to minimum spanning trees, I would expect you to say this was done there, and here is where we add something. This is my own inclination to understand ideas rather than this of the algorithm.
I see, yeah. But I don't know if this like, did you see the connection between them now that I explained a little bit?
I'm not sure.
Yes, these are like strictly harder problems than MSF. So maybe one way to think about this is Boruvka could be like a very simple instantiation of this framework, but the Boruvka's algorithm, it guarantees it's going to take only log n rounds, whereas this algorithm, there's no guarantee on the number of rounds you need. And then, this can have a very, could be kind of inherently sequential in some sense. You still have polynomial parallelism, but
Okay.
it's a much more general problem.
Okay.
And I think I agree with what Shangdi said. Like MSF is like a special case of this framework.
Okay, yeah, because I think that this is a good explanation. Yeah. That's exactly what I was expecting.
Okay.
That you need to the serialization that this may impose that is being bypassed.
Yeah.
Okay, go ahead.
Okay. Right. So as I said, this is kind of more difficult than the Euclidean minimum spanning tree problem because looking for the nearest neighbor is harder. So now I'll talk about how we use ring search to efficiently search for the nearest neighbor of clusters. So in the previous work, the way that you search nearest neighbor of cluster is you just scan a row in distance matrix, right? And that's the method that's used by all of those previous methods. But however, there are two problems with this. One thing is it's not efficient as it takes linear work. And second is we might not have the access to the complete distance matrix if we want to use some quadratic memory. So if you don't have the complete distance matrix, you cannot just scan a row to find the nearest neighbor. So what do? What we do is we use something called a ring search, and ring search works by returning all of the points within a given range. So in this example, this circle is the range, and it will return all of those yellow points. And the way that you can carry out the ring search, or one way you could do it is using a KD tree, where it's a binary tree that recursively splits the space into half. Right, and then when you do the ring search, in parallel, you can visit the two children of the KD tree to get a parallel ring search. So for example, in this example, if you start at the root, you can visit the two children in parallel, and actually you can efficiently prune the KD tree traversal by saying, okay, if the bounding box of a node, meaning the smallest rectangle that's enclosing all the points in the node, if the bounding box of the node does not intersect with the range. So in this case, right, this node's bounding box here does not intersect with the range. You can prune the traversal, meaning you do not visit any of its descendants, because nothing in the descendants can be in the range. Right. So now you can then recursively visit the other children, right, and return BCD as shown here. Right. So we can use this range search to narrow down the nearest neighbor cluster candidates, and specifically, actually, even though we have many points in each cluster, you only need to run ring searches on all clusters centrally. The centroid of cluster is just an average of all points in the cluster. And then we only need to compute the distances to all of the other clusters in this range. And we do not need the distances to the clusters that's out of the range, right? Yeah, and then for this cluster to compute the cluster distances to the clusters within the range, you can compute those distances on the fly. And we do not need the distance matrix. And again, we do not have the distance matrix because we also have quadratic memory, and that's why you need to compute the distances on the fly. Any question about it? I'll explain more detail, but so far, any question?
I'm trying to understand the context. So when you compute things on the fly, the idea is that you have the reason for doing it, which is an implementation, right? Well, you will use this information.
Yes. Yes.
I try to read your abstract to make sense.
Yeah.
So is there an overhead, significant overhead in this computation that you need to account for when you look at speedups?
Yeah.
Because you are doing a lot of computation that otherwise you wouldn't do, right?
Yeah. So for at this point of stage, you can just consider we compute distances, compute cluster distances on the fly. Actually, later I introduce another cache optimization where you can kind of cache some of those distances, so you do not have to compute all of them on the fly. But however, you imagine you have very limited space where you cannot even store any cluster distances. Now you have to compute all of them on the fly because of your memory limitation. That's kind of an intuition of why you have to compute the distances on the fly in some cases.
Yeah, because I'm trying to classify whether what you're doing is a compiler work or an algorithm. You see?
Yeah, it's more towards the algorithm side. Yeah.
If it's an algorithm, then it comes with an algorithm.
So maybe so the speedups, maybe you can mention how the speedups are calculated. So against the baselines, right? It's not self-relative, it's it's just absolute speedups.
Yeah.
Also the space, I mean, I guess the goal for not storing things is because we want to scale it to more than very large point sets. And if we stored quadratic space, it wouldn't scale beyond, say, 30,000 points.
Yeah.
So maybe you can mention how large of point sets you're able to analyze.
Yeah, I just like to give an example. If you have let's say like three, yeah. So like if you have some point and you need to store distance matrix, that's quadratic space that you would need. So like even you have 0 gigabytes of memory, you couldn't store the whole distance matrix for a very small data set. But if you only use linear memory and you compute some distances on the fly, now you're able to run this algorithm on much smaller data set. If you do not need a quadratic memory to store the distance matrix anymore.
Okay, I need to understand the baseline algorithm.
Yeah, the baseline algorithm that we compare to is like if you remember the two sequential algorithms that I've introduces like a bit earlier in the presentation. So for both of them, they keep a distance matrix, right? And then they look into the distance matrix to get the cluster distance instead of computing cluster distances on the fly. And when comparing to those algorithms, even if you just run our algorithms sequentially, we're still faster.
I'll say it's a state of the art, and what are people using algorithm? Always the fair comparison is compared with the best thing was done prior to the.
Yeah, like they are the best thing that's prior to our work. Yeah. Like they are in the experiment section, you'll see the baseline that we compare with. And some of them are actually also parallel, but all algorithms are faster. And partially because they store a large distance matrix, so they have a very large memory footprint, and the others because there's range search algorithm that we're using.
Oh, okay, so it depends on how large the problems they try to solve, and then you will present the speed up. So.
Yeah. It's partially depending on the size of the problem. So even as small as like a 10,000 size data set, we are still significantly faster than.
Okay. I'll wait for your result. I just wanted to put some context. So,
yeah. Okay. Cool. Yeah. Thanks for the questions. Okay. Any other questions?
Yeah. I don't want to slow you down, but I'm a little confused as to how we're able to do like the range search just on like linkage criterion, like for average linkage that makes sense, but like complete linkage, I'm a little confused.
Yeah.
The distance from like the furthest thing in the cluster to everybody else, but that'll be different for different points.
Yeah, I'll show how we do it in the next few slides, but if you still have questions, I can like draw it on the chalkboard. Yeah. Okay, cool. Right. So now I'll explain how you are actually able to just run range search on the centroids instead of all of the points. So here, imagine you have a chain that's running from A to C, and maybe C is some cluster that just got merged. So now you need to find the nearest neighbor of cluster C, right? So how to do it? And now let's use this like X bar to represent the centroid of the clusters. So here, imagine your range looks like this. I'll explain how you get this range in a second. But basically, now you see that the centroids of A and B are in the range, and the centroid of D is not in the range. So now you only need to compute the distance between C to A and B to find the nearest neighbors, because the nearest neighbor must be either A or B. It couldn't be D. And now how do you get the radius of the cluster? So the radius of the cluster depending on beta, which is distance between C and its predecessor A. So that's the cluster that's previous to it in the nearest neighbor chain. If there are multiple clusters that's a predecessor of A, you could just choose the one that's closest to C. And if C currently has no predecessors in the nearest neighbor chain, you can just use a heuristic where the beta is distance to the cluster with the nearest centroid. Right? So this is like a heuristic that you could change it to like any other cluster would work, but it works better or more efficient if it's a cluster that's closer to C. And the relationship between beta and the radius R is different for each linkage criteria. So for edge linkage and complete linkage, actually a bit simpler. It's just R is equal to beta. But for warped linkage, it's a little bit more complicated. So there's some theoretical derivation in your paper saying why this is true. But here is the formula. So are you still confused about why this would work?
No, I think I've got it. I'm a little bit confused for like single linkage where like, the closest point in D is still within the cluster, but I believe that it works and I think I've got it more on the.
I see, like in the single linkage, it would still work because like like in single linkage it would like still work. Yeah, but actually in single linkage, you can obtain a much faster algorithm than running this. So you might as well just, actually, we have another paper on Euclidean minimum spanning tree, and you can just use that instead of this framework. Yeah.
So is this a worst case type solution or is it a heuristic, what you are describing?
You work it, yeah, this, what do you mean by worst case?
Yeah, but it sounds that you are now skipping to heuristic.
Yeah.
So I'm a bit confused in how you mix here elements which I would put as classic algorithm, parallel algorithms, etc., when you try to solve a pure problem correctly in full, versus trying to mix and match hacking tricks, which sounds more like I don't know, I'd call it probably performance engineering, which I know that at MIT is a big deal, but I'm not sure if any other place that does that.
Yeah.
So, which is, it's. I'm going back to my skepticism about the ability of the broader community to bind.
Maybe you could explain what the heuristic means, Shangdi. So, like, you said it's a heuristic, but maybe you can unpack what that means, right? So.
Like in some sense, it's right that you said this is the performance optimization, meaning it optimizes the performance, and that's what the heuristic means. It's still correct. Like it doesn't make the solution approximate, it still gives you the exact solution. It's a heuristic in the case in the sense that it doesn't improve your worst case complexity down. That's what the
no, for the original problem I understand, but the way it sounds to me is like you throw the whatever you have in the kitchen sink, and which of course makes sense when you don't solve practical problems. That's what practitioners do all the time. And you're trying to classify this as and the heuristics are of course a big deal in the both fields, but
but I guess maybe a more similar analogy is, let's say like you do nearest neighbor search using KD tree. That's kind of also a heuristic in the sense that in the worst case, it has linear time complexity, right? But in practice, it improves your running time by a lot, and people all use it. So I think this is a heuristic in a similar flavor, where you use some optimization to kind of in practice improve your running time by a lot, but it doesn't kind of give you a worst case runtime improvement guarantee.
okay, fine. Go ahead.
You buy it a little bit now.
Okay.
Yeah. Any other question? Okay. Cool. Yeah. So now questions, can we do better than this? Right? Because it's sorry, I didn't get your name before. Yeah. We should Uzi. Yeah. As Professor Uzi mentioned before, right? Like if you compute things on the fly, it can still be expensive. So how can we do better, right? Especially if you do average linkage, the distance computation takes quadratic time in the side of the clusters. So we're trying to avoid that if you have some memory available. So the way you can do it is you can cache some intercluster distances. So we don't have to recompute everything on the fly. Now that's what we're going to talk about next. So what we're going to do is we're going to cache a constant number of intercluster distances for each cluster. And this accelerates the nearest neighbor cluster search by avoiding many recomputation of cluster distances. And so now the total memory usage will be n times 1 plus s, which is linear. And this s can be a user input parameter depending on how much memory you have. So I guess one note here is, right, so for this general heuristic, right, it's not just specific to CPU. No matter what kind of architecture you use, you could like all use this cache distances heuristic. So now the question is, we said we're going to store some distances. So which distances we want to store and how do we store them? Yeah. So basically for each cluster, we will create a cache table for it. So this cache is different from the computer architecture cache. What we mean is it's a table that caches them, so that's why we call it cache table. And this is implemented using a parallel hash table model. And the parallel hash table would support storing the key value pairs and concurrent insertions, updates, and finds. So here, one example is a cache table for point D would, for example, could look like this. Right? You have a D that's C and it maps to the distance between C and D that's for 2, and similar for E, right? Distance between D and D is 2. And there can also be empty slots. Okay. And now how do we correlate the distance between two clusters? Basically, if you want a distance between I and J, you look for key I in the table of J and you look for key J in the table of I. And if you fail to find distances in both tables, now you compute distances on the fly. And to insert distances into the cache table, you would insert distance to the cache table if your range search, you find that I is in the range of J or J is in the range of I. So in that case, you would store the distances ij, and you would try to store it in both tables. But if one of the tables is full, you just discard that insertion. And that's why you have to, when you do a query, you need to query in both tables because it's possible that the distances is stored in only one of the tables. And finally, you'll update the cache table after merging the clusters. So now, any questions so far? I will talk more about how to merge the cache tables in the next few slides. Yeah. Yeah. Let's see here. Yeah. If your S is smaller, basically you'll have, or like up until some size, if your S is smaller, you'll have to recompute more because there's a higher chance that you'll have to discard an insertion because you don't have enough slots in the cache table, right? Does that explanation make sense? Let's say like if your slot is 10 and your range search has 10 other clusters, now you can store all 10 distances in the table. But if your S is 3, now 7 of them has to be discarded. If you want to use them later, you have to recompute them. So having a larger S would give you performance of like improvements because you can now store more distances. Yeah. Okay, so I'll continue to talk about merging of the table. Yeah. So now suppose you have cluster A and B and they got merged. How do we update our cache tables? Let's suppose your table A and B look like this. And now you'll create a new table. Or like in practice, you could just put this table, use this table to replace one of those tables to save more memory, but for illustration purposes, let's say you have a separate table. And we again use the last Williams formula to update. So we're still using a complete linkage example, so it's just the max. And you can see that the distances from A and B to C, you can just compute it directly, right, using the existing values that you have. And now, if you want the distance between A, merge cluster A union B to C, you'll find out that, okay, I have the distance between A and B, that's 2, but I don't have the distance between B and D. So now you have to compute the distance between B and D on the fly, and then update the distance here. And similarly, you do that for E. It's possible that you have more keys in table of A, B than the available slot. And in that case, you just have to discard the extra keys that you have. And currently, like whichever you discard is sort of like random, but it's possible that you can use some heuristic to say like I discard something that's likely to be more far away. Yeah.
So this doesn't affect correctness, right? It's just
Yeah.
purely like a performance engineering
Yeah.
optimization.
Yeah, exactly.
Like I guess the correctness guarantees that we always get the dendrogram that the exact sequential algorithm computes. There's no approximation.
Yeah.
And then the worst case bound on the running time is n cubed. I guess you'll mention that.
Yeah.
Sorry, and so when we're doing this merge, is this like you take the max for doing complete linkage, or we always take like for average the same?
No, yeah, this is the complete linkage last Williams formula. For average linkage and worst linkage, you use the corresponding last Williams formula.
Oh, sorry.
Yeah, maybe I should add a note that says this is for complete linkage. Yeah.
I'm still looking up a little bit.
Okay, any other questions? Okay. So now there's just some heuristic or intuition explanation of why this works well. And the reason is, let's say we insert CD and CEF into those tables because CD and EF are in the ranges of A and B. And what does that mean? That means they are close to A and B, right? The other clusters. And that means when you put them into the table of A union B, those clusters are still the clusters that are likely within the range of A union B. And that's why it's likely that in your new range search or your new computation of the nearest neighbor of A union B, it's likely that you will use or your required distances of the ones that you've stored here. And another way that you can look at this is it's a memory saving trick by delaying the computation, the distance computation between points. Right? Let's say you have point P in B and you have point Q in B. In your first round, you might not even consider the distance between P and Q because like P is far from Q, but Q is far from P. And you only need a distance between them when you're computing the distances between cluster B and B on the fly. So sometimes you delay the distance computation between P and Q from the first round to this round when you're kind of just merging the right. Okay, cool. So now I'll talk about experiments. So here are the baselines that we compare with. They are the state-of-the-art baselines at the time of the computation of this. So one is a parallel nearest neighbor algorithm by Zhu and Yun. And the differences between ours and their algorithm is first, they are not a round-based algorithm. So they actually require a lock on distance matrix computation, which can make runtime worse. And the second is they do not have a range search optimization. So they still store distance matrix, which requires quadratic memory.
What architecture did they aim at?
I think for both of those works, they are aiming for like a multi-core CPU, the same as what we are aiming for. And they also run their experiments on the same machine as ours for the experiments.
What I call CPU, I find it a bit surprising that they didn't aim at larger. But you know, if you say I take your word for it. Just remember the spirit of what people did at 2014. I think that try to aim at larger architectures.
There was one paper that did nearest neighbor chain for distributed, but the running times were like very bad.
No, I'm not trying. What I'm trying to say is that it's really incomparable because they are it's like comparing apples and oranges. You understand where you are trying to go, and so
I guess I would say it's interesting. I mean, maybe multi-core is a natural fit because the algorithm it has many rounds. Mm-hmm. And each is very fine grained, potentially does a very little work, right? So, basically when you run in a distributed architecture, the latency and the synchronization costs kind of kill you.
Yeah, I'm not disagreeing.
Yeah, so maybe that's some explanation for why they also looked at multi.
Oh, so you believe it also?
I believe like this algorithm is not necessarily a very good fit for distributed just because of the large number of rounds.
Okay.
Okay. Alright, so the two that we compare is about the next is coding versus global nearest neighbor parity graph. Where I guess to expand that a little bit, I think for like their algorithm, especially the one where it works global nearest neighbor parity graph is ±1 round, so that's like obviously a large round. I think the other thing why it might not be a globally distributed is you're running distributed, you have to somehow partition the distance matrix and then send it to different workers. But distance matrix is like very large. So that's another reason why the communication cost can be really high. Yeah. So experiment speedup, we're running our experiment on 48 core machine, and we use the still plus parallelism. And for data sets, the dimensions ranging from 2 to 16, and the size range from 10,000 to 24 million. And we have synthetic data, real world data, as well as the simulation data that we run on.
What year is this machine?
What year?
Yeah.
There's like an AWS machine that we use.
No. What I'm trying to ask is that, Intel has discontinued many things. So when you describe that, I know that they discontinued for Civic, right? So from what year is this?
I see.
You talk about, I don't know, the Intel Platinum 8275 CL. What year is that, and how does it?
Apparently it was released in Q2 2019, so pretty recent, like 4 years old. Yeah.
Okay, so this was after they cut the Xeon 5? Because what I'm trying to understand here, Intel, which supports all of them, decided to discontinue a certain direction. And there was a lot of work among academics on something that was discontinued, and I'm trying to understand where this connects.
Sorry, Uzi, I missed what you said. What did you say that what did you say that discontinued?
Xeon 5.
Oh no, this is post Xeon 5. This is much later.
That's what my question is.
Okay.
My question, and then this type of architectures, are they continuing in the same vein?
Yes.
Like, okay, no,
To be more general, this is just to explain what we use, but you could have swapped out this Intel Xeon to be any multi-core machine and it would work. You could change cell class to be any with the work scaling parallel scheduler.
because my understanding is it was not anymore native support, like until about 2018.
I see.
So I'm trying to understand where does it stand relative to current architecture?
Yeah.
Does this make sense?
Yeah. No. So I think it's a processor that's in the same spirit as all the latest Sapphire Rapids, etc. So this is a pretty recent processor. It's post Xeon 5, right? So Xeon 5 did some weird things, but then Uzi's right, they discontinued that. But this is not like a Xeon 5 processor.
So the runtime comparison. So this is how we compare it to two baselines. And one thing that I want to note is here on the x-axis you have the number of threads, where 48H means 48 cores is 2 hyper threading, and on the y-axis is the running time. So here, sometimes the runtime kind of does not keep speeding up. It's because we're only running it on a smaller data set, it's only 100K, and on a larger data set, it actually keeps speeding up. The reason we only run it on smaller data sets here is because all of those that keep distance matrix, you actually couldn't run them on larger data sets to do all of the memory issues. And here you can see that all of them, which is this dark or light purple line, is much faster than the smaller baselines. So we have limited time, so I'll try to go faster. So here it just shows that our algorithm, which is this blue bar, is using much less memory than it was realized, as we would have expected because we use linear memory. And finally, this is the parallelism that we get on the larger data sets. The different color represents to or corresponds to different data sets. So in the best case, the computing case, we achieve more than 50 times self-ready speedup for the courses to make understanding. Yeah, I have 2 other slides on experimental results, but since it's close to the end, I want to pause a bit for questions.
So I have one question. So is it open whether we can get quadratic work and the same kind of parallelism empirically from these problems? Or
I think it's a bit hard, and the reason is because of the algorithm, right? But those two get merged. The only case that is invalidated is a single one. Or in a parallel case, because you're maintaining many like of those chains, you can have arbitrarily many other like chains like validated, and that's why it's hard to get the same quadratic time that we got before. Yeah, but I guess maybe you could achieve it by somehow constraining, say, like, I don't maintain all of the nearest machines. I only maintain a smart subset of the nearest machines. Then maybe that could improve the worst case for that. Yeah.
Thanks. Interesting.
Yeah, question.
Does your work with theoretical improvements on this?
Yeah, so the workbook?
The
Depth bound? Yeah, so the depth bound of this would be the number of rounds times log n, or log n log n, because there's like a separate term on the k tree construction. But yeah, this is I guess like better than you have to also consider the work as well, because otherwise if you just okay, I in parallel compute the distances between all the points in every round, you just obtain the depth would be the same as the number of rounds, but then you just explode the work. Yeah. Question?
Yeah, so there's this you do these parallel merges, like multiple merges in a single round.
Yeah.
You can. I know that if you don't add some sort of approximation factor, you can't guarantee that you're going to get like a sublinear number of rounds doing this. But did you see in practice whether this like you end up getting a lot of clusters merged in a given round? Like did it look kind of like a logarithmic number of rounds you would come to then?
Yeah, so in practice number of rounds is pretty small. If I remember correctly, even for 24 million point data set, there's like less than 200 rounds kind of thing. Yeah, like you can artificially construct a very bad case where you got n-1 rounds by having one large chain, but in practice that doesn't really happen. So in practice number of rounds is pretty small. Actually, like if you really want a fine-grained analysis of the ranking time, it will be something that looks like this. Yeah. And in the paper, there are like experiments that show in practice what are like the sizes of A and sizes of D in each round. Yeah. And I don't know what you meant by like approximation, but like the result that we get is the exact same as it's the exact solution.
Yeah, I was saying you allow yourself to get a slightly different tree topology potentially, and you.
I see.
I know in your case you don't.
I see. Yeah. I agree. Like if you make it approximate, you can make the number of rounds even smaller.
Yeah, you can
Yeah.
guarantee.
Yeah, that's true.
Practice,
Yeah.
like if you basically got that, it sounds like in practice.
I mean, yeah, you still got like fewer rounds, but of course, like if you make it approximate, you can get even like fewer number of rounds.
Yeah. I think that a semi-philosophical question is you try to straddle between two dogmas. One is the architecture dogma of making the common case fast. Right? That's what they teach. The theory, well, it's all about worst case. And it seems that when you try to look at speedups, like hard speedups, like the ones you report, you seem to try and mix the two in a way that I think that, to me, the biggest interesting question would be how you want to represent it in an elevator pitch to a computer scientist, with general background, the significance of this work. So I don't think my question makes sense here, but how will you convey this? I'm also something that made a big impression on me. 20 years ago, I went to a game developers conference, and Intel tried to advance. I don't know if you know the VTune. VTune.
VTune? Oh yeah, I know VTune. Yeah.
So, and it was complete flat. Nobody bothered actually spending time when they have a small team developing a new game to optimize it for the next Intel submodel. So I'm trying to understand the elevator pitch of why somebody with general interest in the field would be thrilled by this type.
Yeah, I think for this work, if you kind of want to summarize it into very short, you could say that this is a problem where it's very hard to get a theoretically efficient solution where it gives you great worst case work guarantee as well as a very good like that stuff. But even in that case, are there something that we can do so that it's still accelerated in practice, right? And this is what we have done to try to address this problem. Or even if it does not have a great worst case, or even if this problem is hard to get a worst case guarantee, there's still something you can do, like what we did, like you can use cache tables, or you can use the range for your optimizations, such that for a practitioner who must still only use this on very large data sets, they can now do it, versus before this algorithm, they couldn't do it because of both the large runtime as well as the large memory requirements.
Let's thank Shangdi. Oh, thanks.
All right, thank you.